Yesterday, we introduced Sir Isaac Newton's three little laws of motion. The law of inertia, which is object at rest or in constant straight line motion will remain in that state of motion unless you have a net force. Newton's second law, that's a biggie, F equals ma. Deceptively simple equation, yet very powerful. You're going to see that in a second. And then Newton's third law of action-reaction. Okay? Today, we want to actually apply that to actually learn how to calculate and understand how forces work, and we're going to look at the iron cross in a second. Before we do that, two quick slides of notes. So the first thing is, when you work with forces, you have to draw what's called a FBD, free body diagram. What is that? It's a fancy word for a picture that has all the forces acting on the object. Because until you can identify all the forces acting, you can't really start to quantify the motion that's going to occur. You don't understand what's going on, okay? So for example, let's say this is a picture of a book. Let me grab my physics book. You ask the average person in the street, how many forces are acting on a book just sitting on a table? Okay, most people would say, like, none. Like, what's wrong with you? Like, who cares? Just a stupid book. It's sitting there, okay? You know better than that. There's actually how many forces acting on a book if it's just sitting on a table? There are two. Really? It's two forces on a table, like on a book, just sitting there? Really? And it's actually kind of obvious because I'm holding this book now. You can actually see it more, right? What are the two forces acting on a book just sitting there? There's the pull of gravity, which is called weight. That's a technical term. And we'll look at that in a second on how you quantify and calculate weight. And then how come the book doesn't fall? Because the table is actually what? Pushing up. Does the table really push up? Yeah, it really does. Okay. If the book weighs 5 pounds, -5, the table's got to push up what? +5. So the net force is what? 0, right? If you were sitting there and all of a sudden your book started like jumping off the table, that would be really bizarre and freaky. Because that would mean that the supporting force of the table, the normal force, would suddenly have to be more than the pull of gravity. Okay? So what's cool is most surfaces can support you against the pull of gravity, and it matches exactly that gravitational pull. That's kind of weird. So for example, if you're sitting in your seat and you only weigh like 150 pounds or whatever, your chair has to push up 150 pounds. But if you weigh like 200 pounds, I'm just making up something, okay? Your chair actually has to push up 200 pounds. What would be weird is if suddenly your chair started pushing like 300 pounds or 150 pounds, because you'd be in trouble. You'd either start to sink or fly off your chair, right? So somehow the table and the chair and the ground, it's smart. Okay, there's a little invisible elf called the normal force elf. It knows exactly how much to push up. Okay? Yeah, there's no elf at all, right? It's just a way to picture it. So what happens is as you push on the table or the ground, you deform the molecules like a spring, like a rubber sheet, and then it pushes back to support you. Okay? Now, what if I pushed on this book to try to move it across the table? How many forces now? Most people would say that, well, you had to, you're pushing, there's going to be how many? There should be 3, right? But you know better. You're starting to see the physics here, right? How many forces are acting on a book now if you try to push it across the table? There will be 4. Okay, like, huh? How'd you get 4? I don't get it. Well, if you think about it, if you push on something, it should accelerate, right? It should move. There's a net force. But if I'm pushing on this book and it's not moving, that's kind of weird. How come it's not moving? Because if I push on it, what's going to keep it in place? There's an invisible little force that opposes your motion called what? Called friction. And that's because the surface of this book is not perfectly smooth. If you zoom in with a microscope, you'll see little tiny bumps. And same with your table, right? And so as those surfaces catch and give, you can actually kind of hear that friction there, right? Okay? So one cool way to see the effects of forces and friction is our little air hockey puck toy yesterday, right? Okay? So let me see. Actually, I can't project it here, but I'll try to grab it with my webcam for the little podcast later. There we go. So notice that here there's 2 forces on my air hockey puck, right? The pull of gravity called weight and then the normal force. If I push on it, then there's 4 forces. And in fact, if you listen, can you hear that? You hear the friction, right? There's this little tiny little elf. You can't see them. They're called friction elves. Okay? They're these little tiny ninja elves that are trained by Santa's elite troops to oppose motion. Okay? No elves at all. Just a way to picture it. And here's what's cool about the friction elf. The friction elf always knows to oppose you. So, for example, let's say I push the book to your left or whatever, right? The friction elf's pushing which way? To the right. Oh, I stopped pushing. Who else stopped pushing? The friction elf. Isn't that kind of cool? You're like, whatever. Okay. Let's say I push now to your right. Which way is the friction elf pushing? To the left. You see that? It's opposing. I stop pushing. The friction elf also what? Stop pushing, right? I start pushing towards you. Which way is the friction elf pushing? towards me. Oh, I stop pushing. Who else stop pushing? The friction off, right? If I start pushing towards me, which way is the friction off pushing? Towards you. And I stop pushing. And who else stop pushing? Friction off. Wouldn't that be weird that you're pushing, and then you stop, and all of a sudden it comes towards you like freaky? Okay? So there is no friction off. I'm sorry to pop your bubble. It's just the way to picture it. Now, what's cool about the air hockey puck is when you turn it on, this thing now floats on a cushion of air. So now, who doesn't have any power anymore? The friction off. We've gotten rid of all the friction offs, right? And so now, there are still two forces, but when you push on it, there is no opposing force. You see that? Therefore, the puck just accelerates, and then it can keep moving at a constant straight line velocity because there is no net force. There's no friction to slow it down. Okay? So what's neat is, you actually apply Newton's laws all the time, right? As you walk, as you go about your day, as you play sports, if you play air hockey, whatever, right? You just don't realize you're applying Newton's laws. We're just trying to help you see that there. Okay? Cool, right? So now, let's break down what's called equilibrium. In the word equilibrium is this little root here for equal, okay? If an object is at rest, acceleration is 0, or it's in constant straight line velocity motion, that's the harder one, you're on cruise control, the net force acting on that object has to be 0 because of Newton's second law. So in other words, if something isn't speeding up or slowing down, it's just staying at rest, or it's moving like the air hockey puck in a constant straight line velocity motion, then all the forces have to balance out. They have to equal to 0, the net force. Okay? So in other words, if it's just sitting there, it's going to keep sitting there. That's inertia. It's not going to just suddenly move on its own unless you have a net force, right? Okay? And then the second one that's hard to see in terms of equilibrium is if an object is in constant straight line motion where you're not accelerating. So like you got your car on cruise control, and you don't want to speed up or slow down and get a ticket, and you're on a road trip, right? You want to maintain that speed limit, 65, 55 miles an hour, whatever, right? So if you think about it, a car cruising along, a lot of people think there's no forces, but there are. There's still 4. You still have the pull of gravity, the road holding the car up, and then there's air resistance, so your engine has to apply a force to overcome that air resistance. Otherwise, if you take your foot off the gas pedal, your car slows down. Okay? Next, we got one more quick definition, and that is defining weight, which is the pull of gravity. If you look at Newton's second law, the popular form is F equals ma. It looks like a really simple equation. In a second, you're going to see that this is actually very powerful because you can apply it in more than one dimension, in 2 dimensions, in 3 dimensions, etc. Okay? So the net force on an object is equal to an object's mass times acceleration. The units for force is named after Sir Isaac Newton in honor of his 3 laws here. And mass is in kilograms, acceleration is in meters per second squared. So the definition of a Newton is if you have 1 kilogram of mass, this is a kilogram right here, okay, which is about 2.2 pounds. We're not used to it, but the whole world uses this for their metric system of quantifying matter for mass here. If you have 1 kilogram of mass and you push on it with 1 Newton of force, it's about 1/5 of a pound, it will accelerate at 1 meter per second every second, or 1 meter per second squared. Okay? That means pretty much absolutely nothing to you. That's okay. Let's try to break it down for you, okay? So mass is the amount of matter in an object, how much stuff is there, and it's quantified in what's called a kilogram. And ironically, the standard for a kilogram, it's just this big old metal, chunk of metal, and it's kept in like 2 museums, I think. There's one in France and one somewhere else, and that's like the international standard for what a kilogram is, okay? So we're a little bit confused because we don't use the metric system, but as the world becomes more international and globalized, you will have to learn how to survive in the metric system, okay? Just because hopefully in your generation we will become enlightened and move to the metric system. But anyhow, okay, if you look at this, F equals ma, if you want to define the pull of gravity, well then weight is our force, mass is mass, and then acceleration, we're just going to use g for gravity. So weight is just a special case of Newton's second law. But in this case, we're talking about the net force of gravity. So the units for weight should be technically in newtons, okay? And how do you weigh something? You guys ever see one of these before? You guys ever been to the grocery store? Yeah, and you buy bananas? In America, okay, we're a bunch of rednecks. We ain't use no metric system. What is our scale in America when you buy bananas? It's in pounds, right? You go to any other country in the world, it's going to be in kilograms. But technically, it shouldn't be in kilograms. Kilograms is a measure of mass, okay? Weight should be in newtons because weight is a force. It is a pull of gravity. So how do you find weight? You just multiply mass times gravity. 1 kilogram, and what's gravity on Earth? negative 9.8 meters per second every second. So 1 kilogram is 9.8 newtons. You see that? Okay. So that's kind of nerdy. Okay. Most people don't use newtons. They're not used to that. They still report, like on your driver's license, if you travel abroad and you study in another country, let's say in college, your weight, it should be your mass rather, is reported in kilograms. But technically it should be in newtons. Okay? Which you just take your mass and you multiply by 9.8. So you're saying, I still don't get it. What's the difference there? Well, here's what's tricky here, okay? Your weight is not your mass. They're related. The amount of mass here affects how much weight is being pulled on the spring, which then gives you my reading. You see that? So a way to compare and contrast weight versus mass here. Am I going too fast? Weight depends on the acceleration due to gravity, okay? It depends on how much mass is there times the acceleration due to gravity, mg. Your weight depends on where you are. So right now it's not a big deal. Most of us don't travel into outer space. But in your lifetime, I think space tourism is going to happen. Actually, it's already happening. There's a crazy guy in Arizona. I don't know if you heard about him. He's building his own spaceport. And they're already selling tickets. You can pre-order one for 2018 or something like that. For $200,000 if you have that sitting around. Okay? But anyhow, if you want to lose weight, which is what a lot of people say when they're dieting and trying to get in shape, it's real easy, okay? All you got to do is go to the moon. That's a great example. Because on the moon, gravity is 6 times less. You will instantly weigh 6 times less, okay? So what people really mean is when they want to lose weight is they're not really trying to lose weight, because weight is just the pull of gravity, right? So what they're really talking about is your mass. Your mass is independent of the acceleration due to gravity, and your mass stays the same. It's how much stuff is there. So really, when people say they want to lose weight, what they're really trying to do is just get in shape, right? Lose that beer belly, tone the muscles, and all that. But ironically, I think one of the health teachers told me when you're in shape, muscle actually has more mass than fat or whatever, right? So technically, then you would weigh a little bit more. Whatever. Everyone should just love you for who you are. Okay? Got it? So it's a technical definition. We don't want to get confused. Weight should be in newtons. Mass is in kilograms. And it's confusing, especially because not only we're not used to these physics terms, but we also live in America. So maybe one way to help you kind of picture all this is a kilogram is a technical definition of mass. Okay? A kilogram is about 2 pounds. Technically, it's 2.2 pounds. Okay? And that's just good to know. What's confusing is mass is in kilos, weight we do in pounds. They're not the same thing. Weight is a force. Mass is a quantity of matter there. Okay? But it's just kind of a way to quantify it. So a kilogram is 2.2 pounds, which is about 9.8 or 10 newtons. Therefore, 1 pound is about 5 newtons, or newton is about 1/5 of a pound. So the way to kind of picture this all, because you're not used to newtons or kilograms, is if you go to McDonald's and you want to order a 1/4 pounder with cheese, by the time they cook it, it's only about 1/5 of a pound. So technically, you could go to Canada and go to a Mickey D's there and say, hey, I would like to have a Newton burger, and you would be correct. That would be about a 1/4 pounder with cheese, but they'd probably look at you like you're weird and say, go back to the States, eh? Okay? But anyway, that's just a